Okay, so thanks a lot, Helen, for this introduction. Also, thank you for all the listeners here for joining. I've been really looking forward to this. I guess all of you have some relation to SWEP, but short, we are one of the leading BPHE, the brazed plate heat exchangers manufacturers. We have a 40 years history of supplying heat exchangers for various heating and cooling application. That's heat pumps, refrigeration, air condition, chillers, where we supply both evaporators, condensers, the superheaters, preheaters, economizers, etc. We also have a large chunk of the boiler applications where we then supply the secondary heat exchanger for heating tap water, also district energy, substation, pressure breakers, etc. And then about 20 years ago, we expanded a lot into these industrial applications with oil and jacket water coolers, air dryers, fuel oil coolers and heaters, and then also hydraulic thermal oil coolers, etc. In the last 10 years, we've been moving more into this business, also focusing more to the heat recovery, been also strong in the organic Rankine cycle. We also supply their evaporators, preheaters, condensers, recuperators. And to the right is a picture of a typical engine oil cooler or a jacket water cooler. This is our XL range, the second largest, with 4-inch ports. This one you see here is quite compact, but it still has a capacity of about 1 up to 2 megawatt oil cooling capacity, depending on if it's an oil or water cooler. And to the left there is, of course, myself. I've been here now a decade with SWEP. I focus only to the industrial applications. And with this also, we have also responsibility where we then investigate more about our own products, finding the boundaries and the capabilities. So this is what we will look at today. The agenda is to look at our mechanical fatigue testing when it comes to pressure pulsation testing. We have this thermal fatigue testing, also have a shock and vibration testing, and then some SWEP projects, a bit short about the approvals, and also the topic lifetime predictions and what we have done in this area. When we talk about the pressure pulsation from a mechanical fatigue, we have a setup typically showing in the picture on the right, where we have a possibility we run 4 parallel test units. There's a pump and an oil tank. We have an oil cooler, also of course a SWEP oil cooler. And you can see we have one circuit with a static pressure, and then the other circuit is one where we have the dynamic pressure. And the standard SWEP testing is we have 0 bar initially, and then we increase the pressure at a certain sinus shaped pulse. And within this SWEP testing, we create a valve shot, and basically we test the heat exchanger at 7 different pressures to find how many pulsations they will last before we get a leakage. The lowest pressure we test is where we reach 2 million cycles without failures. This is where we stop testing and consider the heat exchangers to last. You can also do a single point testing where we test the 4 units at a specified known working point, or we do it at the design work pressure, for example. And then we get the chart showing on the lower right side here. Alternative testing can be that you have an initial pressure, and then we pulsate that pressure, plus minus 10, 20, or 30 bars, for example. We also do this testing when we have some new product developments or if there's a specific market requirement, we see usually as a general trend about 500,000 cycles at the operating or design work pressure. We also do testing when we create new products where we phase out the old product to make sure that we have equivalent or better performance. We also do this testing when it comes to certifications, certification test, for example, according to this pressure vessels, a European directive, where you do a certain number of cycles and then you end it with a burst head. Or for example, the UL testing, where you run much higher number of cycles and then you end it with pressurizing with 3 times the work pressure, or you do a test with 5 times work pressure before burst. And these pressures are then also depending on what the refrigerant you are using for the heat exchanger and what approvals is needed. And just showing a larger graph of this Velo chart. For example, you can see how one of our units, B35T, how many cycles it would withstand at being pulsated at 0 to 35 bars. You can read it off the chart, that will be about 200,000 cycles. This chart we can also then use for when it comes to cumulative damage analyzed to predict a lifetime. So depending on how accurate the operating conditions we can be giving, for example, for a condenser for a heat pump, depending on which mode, if it's running for heating or if it's running reversed for cooling, and what pressures it will be operating at, then going into defrost mode. So if this can then be specified during a 10-year cycle, you can see how many cycles, and you add it up together to get this the relation between the number of applied cycles and then divided by how many cycles that's allowed, taking the number from the fatigue curve. And you add those up together. You should not, of course, exceed 100% of the capability of the heat exchanger. So that's one way to estimate the lifetime from a mechanical pulsation fatigue. Another testing that we have done is from a vibration point of view. There's an approval for a GL, germanium-alloyed. This is a specific test that has been designed for brazed plate heat exchanger, that's BPHE, that's intended to be used on board GL classified ships. So it basically is a test where you have the heat exchanger, it's mounted on the shaker itself, and then you have 1 meter long pipes attached to the heat exchanger, and then they are fixed on the other side. The heat exchanger and the pipes is then loaded with a static pressure of 1.5 of the design pressure with a fluid. And then you have the vibration taking, as you will have quite high loads here on the connections into the interface between the connections and the connection plate or the cover plate on the heat exchanger. And this is then tested in both directions. And it's a fixed test scheme going from 0 to 100 Hertz. And then depending on the weight of the heat exchanger or any other object that's tested, it's also setting the amplitude of the acceleration forces on the vibrations. Another part of the mechanical fatigue testing is this shock and vibration testing, shaker table testing. It's a test that's very well known by the market. It's the tests are well defined because for example, all auto car manufacturers, they have their own designed tests. The question that we often run into is, how is then the heat exchanger actually installed? So if you look, for example, to the picture on the left, you see a heat exchanger. It's fully rigid mounted into a frame. So actually, when you're testing this on a shaker table, you're also testing the frame more than the heat exchanger itself. To the right is a test we did on our heat exchanger. Some more details about this. It's a test we did. It's the standard is taken from a railway application, this EN61373. It's shock and vibrations. And here is the test described here, the shock loads in each of the 3 directions. You go plus minus both directions, so that's 6 shocks that's done on the heat exchanger. Since we don't know exactly in what direction the heat exchanger is mounted, it's been tested here for the highest value for all directions on our heat exchanger. And it's a typical installation. You can see here, it's a heat exchanger we have tested. We have increased the number of the plates to get the most extreme dimensions. We have interface downwards. You have connection plates. So we have the 4-inch ports is actually then facing down, and often it's mounted onto the engine block directly like this. And it's also one of the preferred installations that we have. And we are bracing the connection plates to the heat exchanger simultaneously as the whole unit is braced. And then we have a flat milling on the connection plates, so make sure we have very tight tolerances to the interface to the engine block. So here was a shock and vibration test here, and the vibrations is also going from 2 up to 150 Hertz, and also the amplitude of the acceleration is also defined by the test, and that's a 5-hour in each of the axes. So basically this is a test where we make sure that there's no malfunction of the heat exchanger, but also that there's no separation between the heat exchanger and the connection plates, so that the heat exchanger is secured. When it comes to the thermal fatigue, is as a basis for this, we're looking at the material properties. We then look at the 0.3 millimeter thick object, and that's also representing the channel plate thickness in our heat exchangers. And then we look at the temperature change and what allowed tension you can accept in the material. So we can see here that when you are above 120, the lifetime of the material is very low. It will be a break quite fast. And below 60 Kelvin temperature difference, when you're running then a thermal shock, you're then very well increased in the lifetime. So this is the data we have then used for our thermal fatigue testing. What we did a few years ago is that we have built our own thermal fatigue test rig. It's I would say it's a one-of-a-kind rig. It's built fully to our specification. You can see to the right that you have a supply of the hot media and the cold media, and then you have a valve so you can alternate it. We are running the heat exchanger in both circuits. So what we have created is this SWEP standard test procedure, is where we have, taking us from the chart on previous slide, we have the temperature difference of 90, 105, 120 K. And then we are alternating the hot and cold, and we are using both channels in the heat exchanger. So the one fluid is standing still, while the other is then being pumped, the hot one, and this is done 1 to 3 minutes depending on the total mass, metal mass, and also the volume of the fluid or the other side. So everything is then being heated up, and then we close the hot loop, and then we shock it thermally by opening the cold water then into the heat exchanger to get the thermal shock here. And worst case, we will expect somewhere around as low as 500 cycles and then going up to 15 15,000 cycles. So it's very time-consuming testing, but it has been improving now, the test rig. It's working we get good reliable data for this one. There's also a secondary test, we call it the quick cycle, and this is where we then alternate the hot and the cold fluid in one channel only, and the other channel is then open to atmospheric. It's a shorter time because it's less time needed to heat and cool the heat exchanger. It's also easier to find the leaks because it leaks into the other channel, which is then open. It's also been used by some other BPHE manufacturers, but we think it's not really representing the true operating conditions, because you should have a media on both sides, because it also slows down. It's a bit slower, the process of heating and cooling. And from our thermal fatigue rig, you can also see it on the picture, we have also 4 steam generators where we then can go up higher in temperature. Some guidelines we have taken from experience here. We have the most important is then to avoid the thermal shock. We have a ramp-up time then estimated to be about 5 Kelvin per minute to make sure everything is heated up nice and slow. We have the temperature difference. There are 2 ways to define it. It's between the inlets. So if you have a high different temperature between the 2 medias, you should always have this slow ramp-up time. Then we have also between the in and outlet in the heat exchanger. We have this defined within our SWEP selection software, which is the SSP, which is used for dimensioning and selecting the heat exchanger. There we are showing also the actual wall temperatures, which is very different depending on what media you have. For example, if we're running a liquid to a gas, we can have a very hot air, but the liquid is then keeping the wall temperatures down. You can compare it as if you jump into very hot water or enter a sauna at 100 degrees. It's one will burn you and the other one will not. So also when we have water that's cooling, this hot gas water should always run continuously during startup and shutdown to avoid this extreme thermal shock. Some recommendations that we have is that you should even out the plate thickness between the channel plates and the cover plates. That's, for example, also our E-units, which have the integrated start and end plates. That's a thinner cover plate. So we will then lower the tension between the channel plates and the cover plates. They will then expand more in the same rate from the thermal expansion. Smaller ports will also make a stronger unit. And also we should always have the media with the most extreme temperature should be on the inner circuit of the plate heat exchanger. We can also build the heat exchanger more thermal resistant by adding more isolating channels to the cover plates. That's also one way to increase the lifetime when it comes to thermal fatigue. Steam applications, which also involves higher temperature, they're a bit more difficult to control, and our heat exchangers is also a bit more sensitive, so we need to have some safety equipment like a vacuum breaker and also a steam trap, and it's a lot related to the condensate control. We have built a test rig for CO2, the gas cooler. It's here we have a typical the heat recovery unit. So from the hot carbon dioxide is being cooled, and then the heat is used for example, for space heating. But here it involves the combination of thermal fatigue, but also the mechanical fatigue. So the temperature case is about 25 of the water, and about 9 case in the test being pulsated from between 100 to 50 bars. And in this test rig, we build it with dual heat exchangers, so we are then alternating between the heat exchangers then instead of wearing the compressor out. And then we have the cooling water running continuously and the compressor then feeding the heat exchanger with carbon dioxide, and that one is then alternating. And we under these conditions we did about 350,000 cycles without creating a failure at this point. And this represents, if you then follow the compressor manufacturer guidelines, where we have a minimum 10 minutes between the start and stop. So that's reaching 6 start and stops an hour. So this is minimum 6 years of lifetime for this CO2, the gas coolers. It's quite demanding application. So this is some of the products that we have done in the last years. I don't know if you have any questions. Just wanted to here to show what we wake some interest in the fatigue testing and also for SWEP what we are doing. That's my last slide I had today. It's quite a short webinar. We are I know there are many people you listening. If you have any ideas or any input, questions, how we test, what you can ask some questions now within this in the chat or in the questions window. If you expand the control panel, you can also email me afterwards. You will get then send out from this webinar, but also with the contact details